Hello, this is a presentation by Group 15 members on the topic Experimental Data Analysis. So when we say experimental data analysis, what this simply means is the process of analyzing and interpreting data that has been collected through scientific experiment. So the process by which data that has been collected through scientific experiment is being analyzed and interpreted is what we know as experimental data analysis. So on this topic, we'll be looking at certain objectives. So these are our learning objectives on this topic. At the end of the presentation, the following objectives should be acquired, and these are the meaning of experimental data analysis, its importance, and the meaning of data itself, types of experimental data, that is qualitative and quantitative data, the difference between population and a sample of population, the difference between a parameter and a statistics, accuracy, precision, random errors, and systematic errors, the difference between uncertainty and error, estimating experimental uncertainty for a single measurement, instrument limit of error and least count, and at the end we'll solve one example under instrument limit of error and least count to boost our understanding on what it means. So we'll go straight to our introduction, which entails the meaning of experimental data analysis, its importance, and what data also means. So when we say experimental data analysis, as said earlier on, it involves collecting, processing, and interpreting data obtained from experiments to drive meaningful insights. And to achieve this, we have to go through certain steps, and one of the steps is you have to clean and organize the data to ensure that it is reliable and accurate. And our second and last step will be you have to use statistical methods to analyze the data and determine any significant findings or trends. So first, what you need to do is to analyze the data and organize the data, and after organizing the data you use some method called statistical method to analyze the data and determine significant findings and trends. After that, you now interpret your data. So that's what experimental data analysis simply means. And we look at the importance of experimental data analysis, which are it ensures accuracy and reliability of experimental results. It helps in making informed decisions based on empirical evidence. And we come to data. So when we say data, data is a collection of facts such as numbers, words, measurements, observations, or even just descriptions of things. So we'll move on to our next subtopic, which is types of experimental data. So basically there are two types of experimental data, that is qualitative and quantitative data. So for qualitative data, we say that one simply it describes something. So it's a descriptive information, and quantitative data, that one talks about numbers. So it's numerical information, and this is a table that shows the various types of data, that is qualitative and quantitative. And under qualitative analysis, under qualitative data analysis, we also have nominal data and ordinal data, and under quantitative data we also have discrete data and continuous data. Let's move on to see what this means. So let's tackle qualitative data analysis first. So when we say qualitative data also known as nominal data or categorical data, are the simplest form of data. Qualitative data describes a particular characteristic of a sample item. The values are non-numerical and most often have no units. Examples of qualitative data are variables such as gender. You say gender, that's male or female, or the grade. Grades as in exams. So grade A, grade B, grade C, or grade D, and so on. So let's look at types of qualitative data, that is nominal data and then ordinal data. So when we say ordinal data, what this means is that data that are created by assigning numbers to different categories when the numbers have no real meaning. So for example, to boost our understanding on what nominal data means, for instance, in a survey that asks for gender, a 0 is often used to denote male and a 1 is used to denote female. The numbers are used simply to represent different categories and have no real meaning as numbers. So in this data, the numbers here, they are used to represent different categories, but they have no real meaning as numbers. So that's what nominal data simply means. For ordinal data too, ordinal data, these are data created by assigning numbers to categories where the order of assignment has meaning. So for example, when the income of a sample is classified as 1 equal to low, 2 equal to medium, and 3 equal to high, here the numbers are ordering, but there is no way to compare 1 to 2 to 3 numerically. So this is what qualitative data basically entails. Let's move on to quantitative data. So for quantitative data, data that are inherently numerical are called quantitative data. So when we say quantitative data, this means data that are inherently numerical. These types of data usually have units. Quantitative data can also be discrete or continuous. So under quantitative data, they are classified into two, that's discrete data and continuous data. So let's look at what discrete data. So when we say discrete data, they are data that are countable. So discrete data are countable, can only take certain values like whole numbers. For example, number of products, number of workers, number of shifts in a day, number of animals, number of buckets, and so on. So this is what discrete data that are countable are known as discrete data. For continuous data can take any one of an infinite number of possible values over an interval on the number line. Continuous data usually consists of real numbers. For example, temperature, concentration, pH, pressure, and viscosity, and so on. So simply we say that discrete data is countable while continuous data is measured. So this is all what quantitative. So move on to our next subtopic, and this is the difference between population and a sample of population. So when we say population is everyone or everything you wish to study in order to make the necessary decision. Often, when we study a population, we are interested in knowing about the different characteristics of each member of the population. These characteristics are known as variables. A variable is a characteristic of each member of the population. So, and this is so population simply is everyone or everything you wish to study in order to make the necessary decision. So we come to look at what a sample also means. So a sample is a piece of population. If you take a sample, you take small piece of the population and look at it or test it. So population is everything, but a sample, everything you wish to study in order to make the necessary decision. But was sample is a piece of the population. So sample is like a subset of the population. So that's what the difference basically entails. We move on to our next thing. And our next subtopic is the difference between a parameter and a statistic. So when we say a parameter is a number that describes a characteristic of the population. For example, a company that is thinking of adopting casual dress in the workshop would like to know the percentage of employees whose productivity increased as a result of this policy change. The parameter here is a percentage or a proportion. So when we see a statistic is a number that describes a characteristic of the sample. So was a parameter describe a characteristic of the population, a statistic describe a characteristic of the sample. So basically that's what the difference between a parameter and a statistic entails. And statistics can be calculated from the sample data. Statistics that can be calculated from the sample data are closely related to the parameters of interest. The closeness of a statistics of a sample to the corresponding experiment of the population depends on how well your sample reflects the population. So we move on to our next subtopic, which is the difference between descriptive statistics and inferential statistics. So when we say descriptive statistics, as the name implies, is a branch of statistics that involves the collection, analysis, and presentation of data. It is concerned with organizing and summarizing the characteristics of a data. Descriptive statistics is used to describe a population or a sample by using measures such as mean, median, mode, range, standard deviation, and variance. These measures help in understanding the data by providing a clear picture of the data set. And when we say inferential statistics, on the other hand, involves making generalizations about a population based on a sample. Inference is the process of drawing conclusions about a population from a sample. Inferential statistics is used to test hypotheses about populations, estimate the population's parameters, and make predictions about future events. Inferential statistics use probability theory to make predictions about the future events based on the occurrence of past events. So this is what the difference between descriptive statistics and inferential statistics basically entails. We move on to the next subtopic, which is accuracy, precision, random errors, and systematic errors. So in all this, the accuracy, precision, random errors, and systematic errors are known as experimental errors. So when we say experimental errors, what this means is the difference between a measurement and a true value, or the between two measured values. So experimental error itself is measured by its accuracy and precision. So basically experimental error involves accuracy, precision, random errors, and systematic errors. So, but when we say accuracy simply means the measure of how close a measured value is to the true value or accepted value. So the closeness of a measured value to the true value or accepted value is known as accuracy. And when we say precision measures how closely two or more measurements agree with each other. So how closely two measurements agree with each other is known as precision, irrespective of the true value. This one measures how closely two measurements are very close to each other. They don't consider the true value, but with accuracy, that one is the measure of how close a measured value is to the true value, but precision is the closeness of any true measurements. It's known as precision. So that's basically the difference between accuracy and precision. And when we say random errors are errors that affect the precision of a measurement. So errors that affect the precision of a measurement is known as random error. And when we say systematic errors are errors that affect the accuracy of a measurement. So that's what experimental error, accuracy, precision, random errors, and systematic errors mean. We move on to our next subtopic, which is the difference between uncertainty and error. So when we say uncertainty results from random errors and describe the lack of precision. It may express on a fractional or percentage base. So this happens as a result of lack of precision. So the fractional relation of uncertainty is uncertainty over the best value, and the best value here is the value being concerned. Let's say the true value or the accepted value, and the percentage expression of uncertainty is equal to uncertainty out of best value multiplying 100%. Let's come to errors. Errors may be defined as the difference between the reported value and true value. So error here is the expression for error is simply reported value minus the true value. So error results from systematic errors and describes the lack of accuracy. So uncertainty lacks precision, whilst error lacks accuracy. So the error may be reported as fractional error or percentage error. So the mathematical expression for the fractional error or relative error is equal to error over true value, and that of the percentage error is equal to error all over true value times 100%. So we'll move on to estimating experimental uncertainty for a single measurement. So any measurement you make will have some uncertainty associated with it. No matter how precise your measuring tools, how do you actually determine the uncertainty? And once you know it, how do you report it? So no matter how no matter how precise your measuring tools are, there should always be error. This error is as a result of nature, like for example, temperature, atmosphere, weather conditions, and all those stuffs. So no matter how precise your measuring tools are, errors, uncertainty always comes in. So the uncertainty of a single measurement is limited by the precision and accuracy of the measuring instrument. along with any other factors that might affect the ability of the experimenter to make the measurement. So we move on to instrument limit of error and least count. So when we say least count is the smallest division that is marked on the instrument. So the smallest division marked on the instrument is known as least count. Thus, a meter stick will have a least count of 1.0 millimeter. A digital watch, stopwatch, might have a least count of 0.01 seconds. The instrument limit of error, ILE for short, is the precision to which a measuring device can be read, and is always equal to or smaller than the least count. It can't be more than the least count, so it's always equal to or smaller than the least count. Very good measuring tools are calibrated against standards maintained by National Standards Authority. The instrument limit of error is generally taken to be the least count or some fractions. That is to say 1 on 2, 1 on 5, or 1 on 10 of the least count. You may wonder which to choose, the least count or half the least count or something else. No hard and fast rules are possible. Instead, you must be guided by common sense. If the space between the scale divisions is large, you may be comfortable in estimating to 1 over 5 or 1 over 10 of the least count, and this is the common sense you should apply here. If the scale divisions are closer together, you may only be able to estimate the nearest 1 or 2 of the least count. That is if they are closer together, but if they are not closer, you may be able to estimate the nearest, which is 1 on 5 or 1 on 10, but if they are closer, the nearest will now be 1 on 2 of the least count. And if the scale divisions are very close, if the scale divisions are very close, you may only be able to estimate the least count. For example, devices for some device, the instrument limit error, simply ILE, is given as a tolerance or a percentage. Resistors may be specified as having a tolerance of 5%, meaning that the ILE instrument limit error is 5% of the resistor's value. So this is simply what ILE instrument limit error means. So let's solve this example under instrument limit error to boost our understanding of what it means, and also under least count. So the problem here says that for each of the following scales, all in centimeters, determine the least count and the instrument least count and read the length of the gray rod. So here we have to determine the least count and the instrument limit error, and also to read the length of the gray rod located on the rules. So this is the gray rod, and these are the dimensions of the rule of each rule. So let's consider A. For A, we see that so for A, let's find the least count for A. So for A, we say least count is the smallest division on an instrument. So here, this is our instrument, and the smallest division there is 1. So we say our least count is 1, and our instrument limit of error here. So the instrument limit of error here, we say when the scale divisions are not closer to each other, we assume it to be 1 on 2 or 1 on 10 or 1 on 10 as said earlier. So here we can take our instrument limit of error to be 1 on 5, and that will give you 0.2. But when they are closer, as in the case of these stuffs annoying. So but when they are closer, we wouldn't estimate our instrument limit of error to be that. So it may be more than that when they are very close, or it may be less than that when they are very close to each other. So because they are closer, we see our instrument limit, because they are not closer, we say our instrument limit of error is 1 on 5, that is 0.2, and we come to the length. So if we know our instrument limit of error and we know the least count, so from here we see that our gray rod is located above the rule, and it is in between the dimension 9 and 10 centimeters. So in between them, what we need to do is that we have to now count. So from 9 is in between 9 and 10. So we will count the smaller divisions, that is the instrument limit of error, from 9 to 10 at where the rod is located, and add that number to 9 to get our length of the gray rod. So here the dimensions are not made clear, but we can assume it to be at the middle side. So if it is at the middle side, we say our instrument limit of error is 0.2. So we can add about 3 of the divisions for instrument limit of error to 9 to get our length of the rod, and that will give you 3 multiplying, that will give you, and that will give you 3 multiplying your instrument limit of error, that's 0.2, which will be equal to 0.6. So now we add that 0 point, so it means the rod in between 9 and 10, it is 0.6 when read. So it means we will now add the 0.6 to 9 to get our length of rod for A. So if we add that, we'll get the answer to be 9.6. So now the length of the rod for A is 9.6, and that's all what least count, the instrument limit of error, and length of the rod simply entails. And the same thing applies for B. So when we come to B, we can see that the least count here is before 1. Before 1 there's some dimension there, and is in between 0 and 1. So in between 0 and 1, if you add 1 to 0 and divide it by 2, if you take the average, you get it to be 0.5. So we say this dimension here is 0.5. Is 0.5. So now our list count there is 0.5. Is 0.5. Is 0.5. So for B, we say our list count is 0.5, and from our diagram, from the rule, you can see that the dimensions are spaced up small. They are not so close to each other. So if that's the case, we can also estimate to the nearest 1/10. So we say our instrument limit of error for the row B is 0.1, and that, so if you know the instrument limit of error for B, we can quickly find for that of the length of the rod. So but we know that in between 8 and 9, the rod is lying just in between them at the middle, at the midpoint between 8 and 9. So that case, that makes it easier since we know our list count to be 0.5. So quickly we add 0.5 to 8 to get our length of the rod, in which will give you 8.5. So the same thing applies for C. So for C, we'll get our list count to be 0.2 and our instrument limit of error to be 0.05, and then for the length, we will get it to be 11.90, and this is the solution we are talking about. And that's all for our presentation. Thank you very much. See you again. Bye.